So in this lesson, what I want to talk about are types of discontinuity. Now, from the last lesson, we spent a lot of time talking about continuous. So in this lesson, again, I want to answer the question of what are the different types of discontinuity. So I want to just real quickly talk about what is a discontinuity. A discontinuity is a specific x value for which the function is not continuous. Now, that's the thing. Discontinuous or discontinuity is the opposite of continuous. Now, in the last lesson, we were talking about the limit definition of what continuous was. So now, when I do types of discontinuity, I want to talk about the limits there as well. One of the things that I want to handle real briefly, though, is a specific case where something is not going to be referred to as a discontinuity for a reason. So, here's what I'm going to do. I'm going to draw real quickly the square root function, okay? So it goes through 0, 0, goes through 1, 1, and then it goes through 4, 2. So my square root function kind of looks like this. Now, we would not refer to this negative side as a discontinuity because it's not a specific x value, it's a range of x values. So let me repeat again. A discontinuity has to be a specific number. It has to be a singular value for x. Now, let me repeat again. We were talking in the last video about this is continuous for everything from 0 to infinity because it contains all of those numbers and the limit exists and is the same value as the function. But again, it's not discontinuity back here on the negatives because it's a range of values. I want a specific value. So here I go. I'm going to go ahead and look at my first example, my first type of discontinuity. So in this case, we have the function x cubed plus 2x squared minus 3x over x minus 1. I went ahead and graphed it. It looks like this. Notice you cannot plug in an x value of 1 because 1 minus 1 is 0, and you can't divide by 0. However, if you were to approach this analytically, you would factor the numerator, and you would see that there's a common factor in the numerator and the denominator that would cancel out. So what you would have is a function whose limit exists. You can find the limit. However, it's undefined at that number, at x equals 1 in this case, okay? So what we end up with, and I'm going to write it over here on the board, is a thing that we like to call a whole. Notice it is continuous for all of these x values over here. Negative 4, I got 4, negative 3, I got 0. It's continuous for all of these numbers, but I have an empty dot, I have an open dot, a hole, where the graph should be at 1, 4. Now, because I have a specific x value where it is not continuous, I'm going to call it a discontinuity at x equals 1. Now, the question is, we're going to talk about different types. What type is this one? Well, we call it a removable discontinuity. Okay? The reason we call it removable is because I can fix it. I can fill in that hole. Okay? How do we do that, you ask? Well, simple. I'm going to take the function x cubed plus 2x squared minus 3x over x minus 1, where x is not 1, because again, we can't plug in 1 into this function. And the other thing that I'm going to do, I'm making it a piecewise, is I'm going to say whatever the value of this hole is. In this case, it's 4. That's my y value. So I'm going to say it's 4 when x is 1. Now, this fills in the hole. So all of this blue stuff comes from this first part. It's x cubed plus 2x squared minus 3x over x minus 1 if x is not equal to 1, but the whole is going to be 1, 4. It's going to be 4 when x is 1. So that fills in the hole. Again, that's why it's called removable, is because I can fill it in. I can fix it. I can make it right. I can make it WHOLE. I can make it whole. Notice, again, the open dot was called HOLE, a hole. Whole versus whole. Be careful. All right. The other thing I wanted to make sure I mentioned is the definition. So I'm going to go over the definition of a removable discontinuity real fast, okay? So, a removable discontinuity looks like a hole in my graph. So we're going to have an open dot at where it connects, okay? So, like I said, we had a hole right here, and it continued on both sides of it. So that means that my limit as x approached that number, in this case 1 of f of x, was some number. It existed. Both the left side and the right side were the same thing, and so my two-sided limit exists. However, if I were to plug in the number n, or in this case 1, I don't get that same number out. So, let me repeat one more time. The limit as x approaches n, the double-sided limit of the function, exists, and it's a specific number. However, the value of the function at that point is not the same number. So, hopefully that helps explain removable discontinuities. We're going to do some more of these in a little bit. Come back, we got more examples.